I'm going to talk a bit today about the science, about what we know about climate change and how perhaps we might want to understand what the changing climate means for resilience, adaptation and development in Africa. So this first slide, I've probably seen this lots of times before. This is a global average temperature anomaly. So it's a measure of the average temperature of the globe over time. It's very familiar, but I'd like to show it to start off with because I think it shows a couple of really important points about climate change. So the first thing is along the bottom axis is time. So it's from the 1850 through to the present day. And if you kind of stand back and look at this graph, this is climate change, essentially. It's this long-term trend. It's the fact that this graph is very clearly has an upward slope across a very long period. But the other thing I think is worth noting from this graph is that it's very noisy. There's lots of ups and downs, the sort of periods where it flattens or goes down. You can see towards a few years ago, we had the whole hiatus. Is the climate even changing? Is the climate temperature seem to have stabilized? But these are kind of short-term periods. So when we're talking about climate change, we're really talking about the very long-term trends. So the climate, the years around the 1850 look quite different from our recent years. But then within that, what we'll experience is lots of different ups and downs from year to year. So the other reason I like to show that plot is because it gives you some context for this one, which shows our climate model projections. So the first part of this graph in grey is the same line as you just saw for a slightly shorter period, but the slope looks much less pronounced, at least in part because we've had to change the y-axis, so rescale the axis in order to be able to fit in it the changes in temperature shown by our climate model projections. And that's what you see from that vertical line to the right. Again, this is probably a very familiar graph, and you're probably thinking, why global average temperature? But again, I think there's a couple of key points about this graph that are worth reminding ourselves about. And the first is that when we look at our climate model projections, so we look at the blue and the red lines on the right, they are on a different scale from what we've seen in the past. So the future does not look like the past. We are facing levels of unprecedented change, and that we really need to, I guess, address the fact that we have a huge challenge facing us, that there is this real scale change in our climate coming. The other thing you can see on this graph is that there's two areas. So there's the red lines with the uncertainty bar across it, and the blue line as well. The blue one is the RCP 2.6. So this is climate model simulations run with greenhouse gas emissions or greenhouse gas concentrations consistent with immediate, sustained and dramatic reductions in greenhouse gas emissions, which will essentially keep us to a world around about 2 degrees warmer than the pre-industrial average. And then the red one is the RCP 8.5, where we don't take all this mitigation activity and we let the climate run forward to a temperature around about 4 degrees warmer by the end of the century. When you look at the end of the graph from 2100, they are very, very different. And that sense of scale, as I was saying, from what we've seen in the recent past, it's huge if we compare the difference between 2.6, a 2-degree world, and a 4-degree world. And so this is really the case for saying we should be mitigating climate change. We should be tackling the causes. But the other thing that I think is worth in this context looking at is the next few decades, really out to the 2040s, out to the 2050s. There's a huge overlap between these two scenarios. What this is telling us is that really we're locked into a certain amount of climate change, and actually the adaptation challenge over the next 10 or 20 years is not really affected much by the mitigation action we take now. It's necessary to take that action, but that will give you the benefits in the long term. In the short or medium term, we might call an adaptation timescale, we are locked into around 2 degrees of climate change, even if we take quite aggressive and immediate action to tackle the causes of climate change. So it's that locked in bit that I really wanted to pick up here. But of course, we are not going to experience climate change as a global average temperature. You don't go outside and think, oh, the global average temperature is warm today. What we will experience is weather, patterns of weather, changes in the normal cycles and the averages that we see. What we saw in that very first graph is that the climate signal is sort of noisy. We get natural variability. We get years, some years are warmer, some are cooler, and they vary about an average. The thing about climate change is that that average is shifting. So if we think about an El Nino year, that might be warmer than average and with associated weather patterns, but that average is also warmer. So natural variability really is compounded by climate change. And what you can see here is just examples of a number of different weather events, extreme weather events that happened in 2019. All of these have some component of climate change associated with them, compounded with natural variability. I think it's also worth noting that these are things that happen in a context. So you can see the Australian bushfires, for example. In the last summer, we saw the Indian Ocean dipole in a strong positive phase. That brings drier, warmer conditions to Australia. Again, warmer than average. The long-term climate change trend means it was already warmer, so you're warmer again. And that long-term warming and the last few seasons of drought altogether accumulated towards the Australian bushfires. But it's also around forest management. And another example would be the Southeast Asian dengue fever. 2019 is the most severe, extensive epidemic of dengue fever on record. And that is in part because of a changing climate. It's partly because conditions are more favourable to the life cycles of the mosquito vectors that carry the disease. But it's also associated with lower rates of vaccination and also different ways that humans have been managing their own environment. So it's all a compound of natural variability, of climate change, and also of local conditions. So one way to think about that really is, I'm a climate scientist, so I'm interested in climate variability and change. I'm interested in rainfall, precipitation, these climate variables. But these changes are happening in the context of lots of other drivers of change. So changes in environmental conditions, ecosystem degradation, population growth, urbanisation. And really what we want to think about in development context is not what the change in the return period of the 99th percentile of precipitation is, but what that means for water, for example, that circle at the top, what changes in water security might mean for food, for energy, economic outcomes, whether that might result in migration or conflict, the political consequences, health outcomes. Really, the questions around climate change aren't about isolating climate change and seeing what will be the difference in temperature or the difference in rainfall, but that bigger question about the population of 1 to 9 billion people surviving, and not just surviving, but thriving on that planet in the 2050s. While the fact that we know that the climate is variable and changing over that time period, and which we're largely locked into. And it isn't really just a question about climate change, it's a transdisciplinary research question. I personally think it's quite helpful to think about climate in risk terms and to think about, as I see in this graph at the sort of small equation at the bottom, think about the hazard of climate change. And I'll talk in a moment a little bit about what the impacts of the changing climate might be, how exposed it might be to those changes in flooding and drought and temperature and so on. But then also thinking about that in terms of vulnerability. And actually, often the vulnerabilities to those changes are just as important as the changes themselves. And we can think about vulnerability in two ways. So first, the sensitivity of a system. So for example, if you did have a drought in a rain-fed agricultural system, that's going to be much more sensitive to that drought than in an irrigated agricultural system. In this case, you might see a dip in crop production associated drought, which would be larger for the rain-fed than for the irrigated. So it's more sensitive. And then the second component is really adaptive capacity. And that's about, if you see in this example, a dip in agricultural production, do you have alternative means to meet your food security needs? So can you go out and buy some food in the market to make up for it? And that vulnerability, how sensitive you are to the weather and how much you can cope with that variability in weather is as critical to climate risk as the actual. But if we think about the climate impacts in the context of conditions, we can look at Africa. This is a project I did just a few years ago where I looked at a number of climate impact models, which are models which run from the climate models. They imitate temperature, rainfall, and so on, and they use them to think about metrics, to calculate metrics which are perhaps more relevant, so drought, flood, crop production, and so on. The first model you can see here, so these are all, I should say, looking at CMIP 5 model projections, so the last large ensemble of climate model projections, run out to the end of the century and for this RCP 8.5, and I ran them to the end of the century with a high emission scenario so that you can see more clearly what this long-term trend is. It emerges more obviously. And I did it for the whole world. I'm just showing you Africa here. All the icons which are red mean a negative impact, and the larger the icon, you get a sense of scale of how large. This one shows what happens if we run some runoff impact models. Runoff is the amount of water available for use due to rainfall, but after we account for evaporation. Evaporation is quite important as the climate warms, of course. What we can see here is the large sort of brown areas across large parts of Africa, which show that the amount of runoff, so on average, the long-term trend is the amount of water become available from rainfall, reducing across most parts of Africa. You can see the Horn of Africa, maybe some parts of the Sahel, perhaps having more positive outcomes, but generally less runoff. We looked then at drought models under the same sort of scenarios, the same conditions, so these things happening simultaneously. So at the same time as you see less runoff, as you might expect, also seeing drought. So this is the frequency, the intensity and duration of drought increasing pretty much across all of Africa. Even places where there might on average be more water available, you'll also see more drought events. Of course, consistent with all of this is rising temperatures. We know this. This is plots showing the change in temperature of the hottest days of the year. And actually, you can start to see in southern Africa kind of a hotspot here of drying and increasing temperatures, particularly in this area. Interestingly, although we're seeing decreases in runoff, increases in drought, increasing in temperatures, also seeing more flooding, because more of the rainfall that will fall in these high intensity events. So I've shown two different types of flooding here. The little houses, icons, represents inland flooding. So this is especially with heavy rainfall events and river flooding, like in tens of thousands. So most parts of Africa are seeing increasing flooding events. And then along the coast, I've highlighted the main cities, and these indicate tens of thousands of people affected by sea level rise potentially. I also looked at some impact models looking at crop yields for wheat, rice, maize. If you look across globally, you see some increases in crop yields, some decreases depending on which parts of the world. And that's the same for the flooding and the drought impact. But across Africa, all the results were negative. So you see a decrease in crop yields in these simulations towards the end of the century, particularly for maize. One important thing about those crop models is that they assume that those crops get sufficient water. And this last set of models that we looked at assess how much water is required by crops. And with the increasing temperatures, crops need more water. So again, you see these brown areas show where there's an increased demand for water for crops just to stay still, really. And even if that increase in water demand is met at a time when there's less water available, we're still likely to see decrease in crop yields as a result of higher temperatures. So overall, you're looking at a large amount of stress on systems across Africa. The central little map there sort of shows where populations live, so that's purple. The slightly brown orangey colours in the middle there are areas which are currently water stressed. I highlighted or outlined in red countries which are in the fragile index list. And those little red people indicate population change. So they're indicating large areas where you get large projections for population increase. So in the context of all those drivers in the centre, you see an additional stress associated with climate change around the outside. But I think it's worth then thinking, so what does that mean? If we're saying that we've got pressure on the systems associated with climate change, so the hazard, the exposure to the hazard we know is increasing, it's really then about what do you do about the vulnerability? And this is a project I did with the World Food Programme where we looked at measures of food security globally on a kind of an index. And what we did was looked at how vulnerable countries were to being food insecure as a result of climate change. So we developed, if you like, a small food system model where we looked at changing climate, and then we also allowed some adaptation. So we looked at changing sensitivity or changing adaptive capacity, and could we compensate for changes in climate? The map in the centre shows at the bottom is the present day, and as you kind of radiate out, you go to the 2050s and then the 2080s. So the reason there's 8 futures is there's 8 different pathways. We can also say 4 different pathways over time. The present day food insecurity mapping maps very closely to where you currently see food insecurity. So we're kind of showing how food security is making, climate is making countries more food insecure today. That's not climate change, that's just climate. So that's how systems are already not particularly optimized for the climate that they have. On the left-hand side is a low emission scenario. So we say, okay, let's just put all our effort into mitigating climate change. By the 2050s, so that first curve of arc, we're gapped to around 2 degrees, as I showed. But then as you go forward in time, the climate doesn't get any worse. It doesn't get any warmer. It stabilizes around the 2050s. And then you can look what happens if you put in adaptation action or not. Essentially, on the far left curve, that is the only world where the future looks better than the present. That's a world where you mitigate against climate change, but you also put in a huge amount of effort towards adaptation. So you reduce vulnerability. You see in the 2050s, the world is about the same. So essentially, adaptation effort keeps pace with climate change, but then ongoing adaptation gets ahead of climate change as we see the climate stabilizing around 2 degrees warmer. I should say in this scenario, this adaptation is really effectively development. We're looking at increasing the economic development of the countries, which means that they can invest in their systems to make them less sensitive and also have more coping capacity when the climate impacts hit. You can compare that if you look all the way over on the right-hand side. This is a much worse scenario. So everything on the right-hand side looks at high emissions. So if we follow that RCP 8.5, we get a world consistent with about 4 degrees warmer. And then we look at if we adapt or we don't adapt. And on the far right shows if we don't adapt and we don't mitigate. unsurprisingly, everything is very, very much worse. In fact, we had to recalibrate the whole scale in order to be able to fit in the levels of food insecurity onto the map. But the one just to the left, far right, shows you what happens if you go through a high emission scenario, but you still adapt. What you see is you go from the present day, it's quite poor. You go to the 2050s, it's slightly worse because even mitigation has some effect by the 2050s, but adaptation is just about keeping pace. But what you see when you get to the 2080s is that if climate change continues to accelerate, adaptation will no longer be sufficient. So I guess what I want to say that the top headline messages from this are mitigation is essential, but adaptation is also essential, that we will not even keep track with the present day levels, let alone meet and sustain and achieve the sustainable development goals unless we invest in adaptation. Climate change means the future climate does not look like the past, and that both mitigation and adaptation are going to be essential. And I think if nothing else, that very last globe on the right-hand side of that last slide just shows you how bad we're really talking about, how large this challenge is. But the globe on the far left shows that the future can be better than the present if we take action. So climate change isn't going to be global average temperature high experience. It will be compounding variability and long-term change, and we'll see a range of impacts, but the consequences really are about as much about vulnerability as exposure to that hazard. It's the action we take to deal with that that's important. And that will be both incremental and transformational adaptation. I mean, the other key thing I think from that work with all the globes was that the present day has huge amounts of food insecurity. Countries are already not optimized to their climate. And so in some cases, it really needs quite substantial change to overcome that, plus the additional stress of climate change. And really good development means, development itself is an adaptation measure, and good development is adaptation which accounts for that climate change.